Hey, yo, what's up guys? Baby Bear 4812 coming at you one more time. Welcome to part 2 of the three-part series in constructing binary trees from various traversals. So in the last video I put up, we did in order and pre-order traversals. This time it's in order and post-order. They're very, very similar. If you can do one, you can very easily do the other. So there may be moments kind of in this video where I reference the last one. I'll try to kind of have some overlap but not too much, just so I'm not kind of recreating an identical video twice over. If you haven't seen the previous one, I would recommend to maybe go back to part 1. It's maybe just a touch more intuitive. I'll leave the link to the whole series in the description below. And yeah, so I'd recommend checking that out first. If you're already familiar with how to do that one and you're just here to see the code modifications, you can skip ahead a bit further into the video where we actually get to the implementation, so you can see the slight difference in how we're coding it out. But again, the logic will be consistent as promised at the start of the series. The logic will be very consistent, so the videos will transition nicely into each other, or so I hope. Anyways, with that said, we're told that, look, we're given an in order and post order, traversal of a tree. We need to construct it. We may assume that there are no duplicates. All right, that's going to be nice for when we're actually building a map, again, like we did in the previous video. And we're given two traversals here, and this is what the tree looks like. I've copied these over here so we can kind of walk through the example and maybe make a bit more sense out of it. So, like last time, the first thing we want to acknowledge when we get these traversals is the fact that one of them alone, in and of themselves, is not enough to tell us how the tree would be built. And the reason it's not is as follows. If you check out the older video I made on how to serialize and deserialize a tree, or a binary tree, what we did there was we kind of went item by or node by node, and then when we had null nodes, we inputted those as well into the serialization, and so that way we could almost create like almost a replicably sized, like, you know, a tree that tells us exactly where we're missing nodes. Like maybe we have a left subchild, but that one doesn't have any children. We don't have that kind of information here. Okay, we're not that privileged this time around. So what we do need is we need to have two different traversals, which if we can figure out how to work them together, we can actually create the tree from there. And the second thing, I guess. Previous item I said was the first thing. The next thing we need to acknowledge is what the breakdown of these traversals is. So the post-order traversal, which again I won't get into in depth in this video, tells us to first check out the left subtree, then the right subtree, and then the root itself. That's why it's post afterwards. The in-order traversal gives us a left subtree, and then the root itself, and then we check our right, because it's in, as in between the left and the right. What that tells us is as follows, or rather what we need to acknowledge is in any sort of post-order traversal, we're first looking at the left. That means that some chunk of this array is going to be, strictly speaking, the left subtree. A certain chunk of it is then going to be the right subtree. And then the final part of it right here is the root. So we actually know the first thing we get for free is that the last item in a post-order is going to be the root of the tree. Similar to how in pre-order, the first item was the first one, right? And what's nice about these examples here, again, compared to the last video, we're actually building the same tree here in the example, so you can see the numbers are just reversed in these traversals. Okay, and okay, so what do we do with that information? Well, we can kind of notice the same thing with the in order, where if we acknowledge, so if we understand where the root is, so our root's right here, it's 3. If I can jump into my in order here, I can clearly say, okay, I understand where my root is now. And since we know what the order is of the in order, we can actually determine that this entire section is going to be the right subtree, and then this entire section is going to be the left subtree. Without knowledge of what was going on here, we could never actually tell, we couldn't tell what this order was. Like, we didn't know where the left and right subtrees began and ended. Knowing this now, I can then jump back and hypothetically go, look, this is then my left subtree, that matches up, right? This is my root, and then it must be that everything else here is the right subtree. And again, the way that we did this, so we determined this, was by saying, I know where my root is. That's the easiest part, because I have a post order. Since with the post order I have the in order, we can determine exactly where it falls, and then say this is my left subtree, this is my right subtree, and then recursively dive into each of these, repeating the process and building out the tree with every step that we take. This becomes slightly less trivial, which we'll see in the next video when we've got just pre-order and post-order. I think it requires a bit more mental juggling to kind of piece together how we're going to do it, but for now, it's still relatively easy. Similar to what we did in the previous video with the pre-order. So with the pre-order, we kind of said our route starts here, and then sequentially we're going to keep walking through our pre-order this way, kind of one item at a time. And with each of those, I would determine whether it was kind of which subtree it fell in, and from there, if we could build a further right subtree or left subtree from that route. Since our route is here now, and really you can think about this question as being the same as the previous one, but backwards, walking backwards through the post-order array, what we're going to do is we're going to say, let me start by actually creating this route right over here. And then what I'll do is I'll move backwards and say, well, this is going to be the, some part of my right subtree, and then we'll keep going, and eventually that falls into a left subtree. But recursively, how we're going to make these calls and how we're going to write the code out, will make it so that if I can determine where I'm sitting, that's where my route is, or rather, I'll be pointing right here. I'll say this is my route, and I'll create this node, and I'll say, okay, let's move along further through this traversal. But from this point, I'm going to understand that I now need to. I've got some sort of barrier. I've got boundaries on where my right and left subtree are going to be. So if I was to say, I started with the 3. I think like last time, what I'm going to do is just erase some of this. Give myself a bit more space. If I was to start and say, so I acknowledge that 3 is my root, and from here, by getting to this index, and by the way we're going to get to this index is we're going to create a hash map to store each of these values, and rather for each of these values where their index is within this in-order traversal, so we're not walking through it every time looking for items individually. I'll understand that my left subtree must begin, if this is my root, then everything to the left of here must be my left subtree. Everything to the right of here must be my right subtree. And I'm going to keep 2 indices for the beginning and the end that we're going to use to pivot kind of which part of the array we're going to be looking at. So here we'd be looking at the left side of the 3, and then here we'd be looking at the right side, which would be 15, 20, and 7. If I can do that without moving my face. Perfect. So I'm not going to be passing in the actual array. We'll just be pointing at the indices, and these indices will kind of look like, maybe I'd make a call right here and a call with these 2 both pointing at the 9. And what we'd say is, okay, we've recursively created our root. We now want to create a kind of a subtree business from over here and from over here on this side. And again, like I think like last time, once we get into the code, it'll be slightly more clear. But this is the general logic behind how we do this. And you can walk through the rest of this example here. You'll kind of see what we end up with. I realized in my previous video I never actually finished this example, but essentially what happens is I'm looking at this 20 here now. So after I make my call, I'm going to acknowledge that, okay, well I'm gonna have to start with this 20 right over here, and once I find the 20, I realize that everything to my left is my left subtree, everything to my right is my right subtree, and we end up with this 15, 15, and 7 business over here. Now, the reason that we're not actually going to be picking up this entire section of the tree is because of how we're going to be playing with the boundaries. So the start and end indices that we're passing in will, once we get into the code and we pass them in, I'll I think it'll be a bit more clear on exactly how it is that we're defining these boundaries, and then based on our terminal condition, why it is that we won't end up kind of almost looping through this entire tree and look in this entire section without just creating this one element here. So I think that, I hope that explanation made sense. As always, kind of let me know in the comments down below if I've kind of left something to be desired and need clarification. But otherwise, we can jump into the code, and like last time, I've got it pre-written out here already, and I want to do that just so the actual the template is consistent and the logic between videos is kind of as seamless as possible for you guys. What we're going to do is begin with our standard error checking, and we'll just say if not in order or not post order, meaning we're given some sort of null or blank values, we're just going to return none. Again, we're not given any constraints here, so I don't know if there's anything else. Nothing else we really need to check for. I'm not even sure we need to check for this, but I'm putting it in there just in case. We're then going to define some sort of builder function, and I don't know if you guys heard that. Somebody dropped something really heavy outside. Like, that did not sound good. Anyways, I don't know what I'm going to, we'll build this function in a second. What we are going to do though is we acknowledged last time and even here that we know where our root is and where we want our starting index to be, and we're going to want to move it sequentially one step at a time. So I'm going to call it post index. In the last video I called it pre-index, here it's post index. And we know that we want to start by looking at the end of the array. So we'll start by looking at the end, which is the length of post order minus 1. The next thing that we wanted to do before we actually returned this builder function, or the call from the builder function, we actually wanted to create a mapping for where all the values fall in the in-order index, or in-order traversal, sorry. So I'll call it in index map, just like I did last time, and I'll set it to an empty dictionary. And super simply, we're just going to enumerate through the in order array. And what we'll do is we'll say in index map at this value. So at any given value I'm looking at, I want to know exactly what index it falls at. So I'll say that in index map of val is equal to index. Now, at this point, we actually want to get into figuring out like how we're gonna build this function. And last time what we did and what we'll do again is we kind of said we wanted to acknowledge that at any given function call, I want to determine where my left and right bounds are on the function that I'm calling with respect to the in-order traversal. So kind of if we want to make the right subtree, I want to know my boundary here and my boundaries here. So what I'll do is I'll call them, again, consistently, I'll call them in start and in end, okay? What we did was we said that there are three conditions for how these two indices can relate to each other. We can be in a position where the start index is greater than the end index, and at that point it's like we've gone too far. It doesn't really make sense. Like we can't start after we end. So at that point we'll return a null node, or just return none. Otherwise, if we get in a position where the start index equals the end index, then what we need to do is maybe I'll do this and I'll say then there's the else, and just so I have this framework built up. At this point, imagine a scenario where we've got maybe there's only one entry item in the in-order and pre-order and post-order traversals. So these two pointers, the in start and end, would kind of be pointing at each other. And the reason they would be here, I should kind of let me start here by we're gonna have to pass in 0 for our start and then the length of the in-order minus 1 as our end. These two would be equal to each other if, let's say, we only had one entry. And so at that point, we want to actually create a node that's called, or rather, it's part of the tree node class, and it's going to have a certain value. That value we're going to get from the post order at the post index that we're currently looking at. We may, if we have other items, we'd have to move that index up by 1, or decrease it by 1 because we're going backwards now in post order. And then we'd actually return the node. So this is almost like our, I guess these two are our exit conditions, our terminal conditions, based on if the start is greater than the end, we're like, hey, this is bogus, we got no children, or this just doesn't make any sense, so we're returning none. And then we will, right here, if they're equal to each other, we're only looking at one item, let's just return that node as it is. It's not going to have any other subtrees, because this is all we got there. There's no other boundary for a subtree that we're making. Now, here, the else becomes redundant, so I'm just going to code it out manually. And at this point, imagine we're working with this example. Imagine we're jumping into this example, and the first thing we said that we needed to do was actually create this root with this value. So I'm going to have my root value I'm going to get it from my post order as I'm walking through the post order, and it's going to be wherever our post index is pointing at. I'm then going to be interested in where this value falls within the in-order traversal. Like right here, the 3 was right here, and because from there we knew how we could build our left and right subtrees. So I'm going to call this root index, and I'm just going to say in index map, and the value we're interested in is our root value. And the reason I've broken these two variables up, just to make it a bit more legible, is so that when we actually create the root, I can just say create root at tree node of root val. And now we've created this root. Eventually, I'm going to want to return the root. And in between, we're going to have to do a bit more work in terms of actually building the rest of the subtree. So imagine now we've created this root here. We've gotten this 3. And what we said we wanted to do next was to move our index over and start walking through the rest of the post-index array. So I'm going to say post-index minus equals 1 because we're moving it to the left, one step at a time. And then I'm going to have to create my left and right subtrees. But let's think about this. Since we're going in post order, right, we've got, we're kind of going backwards. We're looking at the root, and then all this is the right subtree, and all this is the left subtree. So if this item is coming up next, I'm going to attribute that to my right subtree. So I'm going to say root.right is equal to, some builder call, and we'll figure out what that call is. And then we'll see root.left is also equal to a builder call, just with different parameters on where our indices are. The only thing we have left in actually answering this question is to just simply say what are the boundaries within this these index calls for the in-order array. Where do we want to put these boundaries? Well, let's think about this. If I've got, this is my in-order indexes right here. So we call this root index, right? Root index right over here. If this is my root index, I know that my right subtree is going to start at root index plus 1 and go all the way to the end, or whatever the end is of that in-end value. So I'm going to start at root index plus 1, and I'm going to go until the in-end. So wherever we've defined that end at, and that one might be variable as we make our recursive calls. It's going to kind of adjust as we go. Then we think about what the left subtree is. Well, we're going to start at the root minus 1 and go to the beginning, whatever our defined beginning was in that recursive call. So we're going to start at root index minus 1, and that's going to be the end. I apologize. So since we're almost reading this array from left to right, what we're going to do is we're going to start from in-start and go until root index minus 1. And so what I mean by that is this. Imagine we kind of had an array right here here it's of length 1, but we could add more items. I want to say that my start boundary is whatever my start was, and then my end boundary is going to be my root index minus 1. All right, so that's why we're saying from in-start until root index minus 1. And so I'm going to run this to make sure I didn't make any silly errors, which I did as always. Okay, and this is the one thing I forgot to mention. So post-index, it's an unbound local error, and so, excuse me, it says that, I'm going to move this out of the way. Post-index was referenced before assignment. Now, we have assigned it. We've assigned it out here. Post-index does exist within the context of this outer function, of the build tree function, but not in builder. We have access to it, so I don't have an issue just accessing it per se, but we will have an issue if we try to modify it. And so what I'll say is I need to declare it as non-local of post-index, and I think if I run it now, we should be all good. So let me submit that, and there we go. We got all the times there. I'm going to move myself out of the way again, just so we can wrap up and summarize what we did. So this is all the code that you need for this question. Again, I think this one was I know it was really similar to the previous video, so part 1. Part 3 will be different, okay? That one it's a different beast. I think it's a lot harder, but we'll get there. I think actually it might even have a clear explanation that's just harder to implement. What we did was we started by determining what the actual order is of a post order and in order traversal. We just kind of acknowledge that we don't actually know for free what the breakdown is of the left subtree, right subtree, and the root itself. But we can determine the root pretty easily from the post order. From that, we can then easily determine the left subtree and the right subtree from the in order. And ta-da, that's how we kind of think about making these recursive calls and building the actual tree. What we focused on doing was noticing that we just need to walk through the post order array or post order traversal one item at a time. And as we're doing that, we are going to be looking for where that item falls in the in order traversal. That's why we built this map here. Once I see where it falls in the in order, I can then determine what boundaries I want to set in terms of where my left and right subtrees are going to begin and end. We added these terminal conditions in here just to know when to actually jump out. And so again, if our start is greater than our end, we're returning a null node. We don't have any children there. Or if it's equal, we're looking at just one node. And in that case, we're going to return that node, and there won't be kind of any left or right subchildren. So I hope this video helped. I hope the explanation was clear. Any comments, questions, feedback, leave them down below. I'm happy to address them. This was another linear time, linear space solution. If you guys have any other questions, let me know. subscribe, like, share, comment. I'm trying to mix up the order. Yeah, all that fun stuff. And I will see you guys in the next video. Peace.